This is the next video in a chapter on chemical bonding and molecular geometry. We have just finished drawing this beautiful table with all of the different electron geometries along the left and all of the different molecular geometries across going to the right. But one thing that we didn't talk about was as we stepped across the table to the right, replacing a bonding pair with a lone pair, we simply inserted the lone pair into the picture as if nothing else in the molecule had changed, when in fact there are several distortions that occur in the molecule when those lone pairs are added. So let's talk about the top three distortions with lone pairs. So the main idea of this video is that not all electron groups are created equal. Lone pair groups are a bit more picky and they need a bit more space than other groups. So the first main idea is that lone pairs need more space than bonding pairs. Okay, so let's draw some molecules to show what I'm talking about. So here is a molecule where all of the electron groups are bonding pairs, where every slot is filled by an atom. This is methane. And let's compare it with something that has a lone pair in one of those possible slots, NH3, or ammonia. So we can practice our skills of electron geometry and molecular geometry identification here. So we can see that methane has 4 electron groups, 1, 2, 3, 4, and 4 electron groups puts the electron geometry in the tetrahedral category. And when we want to name the molecular geometry, we're only going to consider the bonding pairs, and all 4 of these are bonding pairs. There are atoms at the end of each pair of electron, so the molecular geometry is also called tetrahedral. We can practice for this guy as well. This molecule also has 4 bonding groups, 1, 2, 3, and 4. And for electron geometry, all electron groups are considered equally. We love them all. And for molecular geometry, we're only going to name the shape made by the electron groups that connect to atoms. So these 3 electron groups are bonding pairs, and this electron group is a lone pair. So if we cover up that one and we name the shape made by this structure, this shape is going to be trigonal pyramidal. Or you can look at the charts if you're having trouble remembering. Okay, so now that we've practiced, let's look at the differences between these structures, which may not be obvious from my drawing skills. So we said that tetrahedral structures have an angle of 109.5 degrees between each of the electron groups. In this particular molecule, because this electron group is a lone pair and the lone pair needs a lot more space, it's going to push the other groups closer together at the bottom. So the angle between these groups is going to be slightly smaller. It's going to be 107 degrees. So that's the first difference. We have a smaller bond angle when we start to add lone pairs. Lone pairs need the most possible personal space. The other difference is going to be in the bond length. So the length of a carbon-hydrogen bond in this molecule with no lone pairs is going to be shorter than the bond length in this molecule with 1 lone pair. Because this lone pair needs so much space, these 3 electron groups are going to squish together slightly and they're going to be slightly extended so that these hydrogens are the same distance from each other. So the bonds are actually going to stretch a little bit. So when we introduce a lone pair, the other bonds in the molecule are going to get slightly longer. I apologize for writing over my line. This just happened. Okay, so lone pairs are particularly strongly repelled from bonding groups, and they're even more repelled from other lone pairs. More on that later. So we can sort of rank this repulsion. So we have the greatest repulsion between two lone pairs. So if we have two lone pairs to place in our molecule, we are going to place them at the absolute furthest apart place we can find. The next greatest repulsion is a lone pair bonding pair repulsion, like we have drawn here. This is an example of a lone pair being repelled by other bonding pairs. And the least amount of repulsion is two bonding pairs. Let's see if we can fit it here. There we go. Miracles do happen. So lone pair repulsion is the most amount of repulsion. These groups have to be placed the farthest apart in the molecule. The bonding pair interaction has the least repulsion. So we can put those closest together. So this is why the lone pair bonding pair interactions in the middle create a small shift in the change in the molecule, whereas the three bonding pairs in the picture are able to be slightly closer together because that repulsion is less. So this angle is able to be smaller because of that lower level of repulsion. So lone pairs need a lot of space. So there's something else that needs a lot of space, and that is multiple bonds. Double bonds and triple bonds need more space than single bonds. And if we think about it, that makes more sense, right? Multiple bonds have more than 2 electrons in them, unlike a single bond, which only has 2. So here are 2 structures that are both in the trigonal planar electron group geometry. Let's confirm. So electron geometry, we count the electron groups, 1, 2, 3, trigonal planar. And for the molecular geometry, we only count the bonding pairs. All of these 3 are bonding pairs. So the molecular geometry is also trigonal planar. And over here, it looks a little bit different because one of these electron groups is a double bond, but we count the double bond as one electron group just like we did for a single bond, because this is still one connection between 2 atoms. There are still 3 groups because there are 3 things connected to that central carbon. So this molecule is also a trigonal planar electron geometry, and because there are no lone pairs, the molecular geometry is trigonal planar as well. So far, so good. Okay, so let's talk about how multiple bonds need more space. So we learned in the trigonal planar structure that this angle in between 2 bonds was 120 degrees. Over here, our double bond is going to need slightly more space than the single bond. So this extra space is going to be provided by squeezing these other 2 bonding pairs slightly closer together. So this bond angle is going to be 118 degrees. So that's our first difference. Smaller bond angle. And as we said in the previous one, the other difference is the bond length. So we have a particular bond length for our normal trigonal planar. And when we have a trigonal planar involving a double bond, that bond length is slightly extended. A longer bond length with a multiple bond. And that's because this bonding pair is actually 4 electrons, 2 in each of these bonds, and this bonding pair is 2 electrons. So it would make sense that this bonding pair of 4 electrons need more space than 2. And so if we were to rank things by how much space they need, we would still put lone pair at the top. Lone pair needs more space than anything because it is unrestrained by a second atom. And then the triple bond would need the most space out of all of the bonding pairs, followed by the double bond, followed by the single bond. So lone pair needs the most space, multiple bonds need even more space, and single bonds need the least amount of space. So the model that we made, the big table of molecular geometries, is mostly correct, but when we start to replace bonding pairs with lone pairs, we start to see these slight distortions where the bond angles become slightly smaller between the other atoms, and the bond lengths connecting those atoms start to become slightly longer. And this is consistent and measurable, and that's how we can feel confident in saying that these distortions exist. So in the next video, we will talk about what happens when your molecule is slightly larger and it has more than one central atom, and we will do a full-length example.